Welcome back. My name is Himanshu, and this is the seventh lecture in this course, Bayesian modeling for behavioral sciences. What we were discussing was discrete random variables. So you already seen one of the examples, one of the popular example of a discrete random variable, which was a binomial distribution. So before going further into discrete random variables, let me quickly summarize what we have covered in this course so far. Okay. So we started with the very basic idea that whenever you have done any experiment or you have collected any data, for example, from survey or from web, whenever you have any empirical data, okay, the fundamental assumption in statistics is that the data that you are seeing must be coming from some true generative process. So there must be some truth behind this data, but we cannot directly access that truth. So what we do, we make some assumptions. Okay, so we assume that there is some probability assigner function which is assigning real values to events in your event space. Okay, and this probability assignment must be constrained by three axioms of probability. Okay, so once we have this assumed probability assigner function, we estimate the properties of this probability assigner function, and by extension we try to infer the properties of the true generative process, right? So what that implies is that whenever you want to analyze any data, okay, so whenever you have experimental data and you want to make some theoretical inference of using that data, you would always start with an assumption. Okay, and what kind of assumption is it? You would start with an assumption about the probability assigner function. Okay, so exactly what is the probability assigner function, which is assigning real values, probability values to events in your event space, right? So that's why it is very, very important to understand what is the nature of these probability assigner functions, because whenever you will be doing data analysis, you will need to choose your assumptions. Okay, you will need to make a choice that what is the assumption you are making about the underlying generative process, right? And those assumptions should be reasonable given the kind of data you have and what you think what could be the underlying process behind that data. Based on that, you would make some reasonable assumptions, right? But in order to do that, you need to understand what is exactly the nature of those probability assigner functions. Okay, so that's why our first few lectures are dedicated to this, in understanding what are these probability assigner functions. So first thing that we saw was that these probability assigner functions must be constrained by three axioms of probability, and that we covered in first axiom, second axiom, third axiom of probability, and we saw applications of it, how it is applied, what it implies for the elementary events in our event space. Second, we saw what kind of probability assigner function you can define and what is the role of random variables in it. So we concluded that we always define a probability function on the values of the random variable, okay, not directly on the sample space but on the values of the random variable. That's why you will later on see that we call basically we always talk about random variables. Even when I'm describing these probability assigner functions for discrete cases, for discrete sample spaces, I'm defining them as discrete random variables, right? So let us take a little example. So suppose you want to analyze data from an experiment where participants have to recognize whether a word is a meaningful word or not. Okay, so they have to make a choice whether a given word on a screen is a meaningful word from English or not. So the responses they can give is yes or no. Okay, and let's say we collect this data from multiple participants and across multiple trials. Okay, now once you have data, you want to infer what is the underlying cognitive process that might have generated this data, right? But you don't know exactly, you cannot really know what is the true generative process. So you make some assumption. Okay, now what assumption can we make about this particular data? Okay, so what kind of probability assigner function can generate this type of yes or no responses, right? Maybe there could be multiple probability functions that can generate this kind of data, right? One of such functions we have seen in the previous lecture, which was a binomial distribution. A binomial distribution can generate exactly this kind of data. Why? We will see. There were some properties, right? So because this kind of data follows, we think it follows a certain kind of generative property. So for example, you are getting binary response, yes or no. These trials are independent from each other. So what a participant produces in this particular trial would not affect what they would produce in the next trial, right? So all those assumptions hold. We will see all those in detail as well. But the idea is this, that you will need to make some assumption that this data containing yes and no responses, what is the underlying probability function behind this data, right? So for example, binomial distribution is one such possibility. You can assume other probability assigner function as well, for example a Poisson distribution, right? Once you have made assumption, then you can, using the data, you can estimate parameters of your probability assigner function, and then by extension you can make some inference about the true generative process. Okay, so that's why whatever we are doing so far, this whole process is important to understand why do we need assumptions and what kind of assumptions we can make for a particular kind of data, right? We haven't even gone into the whole inference process yet, but actually we kind of have, because assumption is a very critical part of statistical inference, right? So that's why we are starting with this point. Okay? All right. So coming back to discrete random variables. So the first one that we covered a little bit in the previous lecture was a binomial distribution. Okay. So what is a binomial distribution? So maybe try to recall something from the previous lecture while I write here. Okay. So think of a coin toss example. Let's say you are tossing a coin, let's say 10 times. Okay. What happens in such example? That you can write a trial ID here. So let's say trial 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can write the outcome here. What could be the outcome? Let's say either heads, tails, tails, heads, tails, tails, heads, 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 right? Now you can define a random variable, let's say yi, where I indicates ith trial. Okay, so I have defined a random variable yi. Okay, so yi would take a value 1 if the outcome is heads, and it would take a value 0 if outcome is tails, right? So basically it's your choice in whatever way you want to define your random variable. Okay, so I have defined it like this here. It counts basically number of heads. So tails, so 0, 1, 0, 0, 1, 1, 1, so on, right? Okay. Now these trials hold some properties, right? And what are the properties of these trials? Let's see. Or if I ask you what is the property of this random variable y, okay? So this random variable yi, or these random variable y1, y2, y3, they hold certain property. Okay. So first property is this, that they are producing, that you see, binary outcome, okay, or binary value of the random variable y. Okay, so it can take value 1 or 0. Outcome could be heads or tails. Okay, so there is binary outcome. What other kind of experiment can have binary outcome? For example, an experiment where participants have to produce yes or no response. Okay, correct or incorrect, success, failure, right? So those are all binary outcome experiments, right? Where in each trial, a binary, one of the two outcomes is being produced. Okay, so that is first property. Second, these trials are independent of each other. What does that mean? That whatever happens in first trial does not affect what would happen in the second trial. That means whatever the outcome you obtain in the first trial does not affect the outcome in the second trial. Okay, so for example, if you get heads in the first trial, would it determine whether you would get a tails or heads in the second trial? Really, it doesn't, right? So these trials are said to be independent of each other. Okay, Third property is that they are identical. How they are identical? Well, you are tossing the same coin 10 times. So the coin is identical. And what does that mean? What does that mean is that the generative process that is in action for producing y1, basically the first trial outcome, okay, the same generative process is there for producing the second trial outcome, right? Because it's the same coin and you're following the same process. What is the process? You're tossing it, right? So tossing the same coin randomly, right? So it is going to give you either heads or tails. The coin is same, that means the probability of obtaining, underlying probability of obtaining heads is same, okay? So it is called the identical property. So all these, the underlying generative process in each of these trials is same, okay? So whenever you have such trials which have binary outcome, independent and identically distributed, they are called Bernoulli trials, okay? So we call them Bernoulli trials, okay? So if this is the case, if you have n trials, okay, which are, or let's say n random variables y1, y2, y3 and yn, such that they have binary outcome, they can take binary values and they are independent and identically distributed, then summation of yi's from I is equal to 1 to n follows a binomial distribution with underlying probability of success theta, which is basically, theta is basically probability of heads, underlying probability of heads in a particular trial, okay? You can actually call this random variable x, okay? You can call this random variable x. X is summation of yi from 1 to n, okay? So x is called a binomial random variable. It follows a binomial distribution with theta as its parameter. And what is theta? It's the underlying probability of heads in any ith trial, okay? It would remain same across trial. This theta would remain same across trials because you have the same coin, okay? But what does it mean? What does this binomial distribution does? Well, that for that you would have to see its probability assigner function. So what is the probability assigner function associated with the binomial random variable f of x theta? So this probability assigner function is given by n chooses x, theta to the power x, 1 minus theta to the power n minus x. So this is the probability assigner function. We actually call this probability mass function. This is probability mass function of the binomial distribution or the binomial random variable, okay, PMF. I briefly described why we call it PMF. So we will in fact call PMF, basically all the probability assigner function belonging to discrete random variables would be called probability mass function. So this is the technical formal name for these probability assigner functions. In fact, from now on, I won't be calling them probability assigners. I will be calling them probability mass function for discrete cases and probability density function for continuous cases. I will come to continuous cases why we call them probability density functions, okay? So discrete random variables, I will always call them probability mass function, okay? So for every distribution, you would have an associated probability mass function, okay? So this is the probability mass function for a binomial distribution. So what does it mean? So when you toss a coin 10 times, okay, then this function would give you that what would be the probability of obtaining, let's say 3 heads when you toss a coin 10 times, okay? How would you calculate, by the way? What is the probability of obtaining 3 heads when you toss a coin 10 times? In that case, x, which is the number of successes in this case. What is x? Is the summation of yi. So how many heads you will get? So in this case, x is 3, n is 10. So basically 3 heads out of 10 coin tosses, right? So what is the probability of obtaining 3 heads out of 10 coin tosses, right? But in order to calculate this, you will need another, you need to fix another parameter, which is theta. Okay, so what is the value of theta? So theta will determine what will be the probability of obtaining 3 heads when you toss a coin 10 times. Okay, now this is very important point, because if you have basically, if you have understood probability from high school, you are likely to think that if you are tossing a coin 10 times and you get a heads 3 times, so maybe probability of obtaining 3 heads is 3 by 10 or something, right? But that's not how it works, right? Because probability is not something that you can measure from the data, right? It's not a measured quantity from the data. Okay? Probability is something that is assigned by your assumptions. Okay, so probability is not being measured from the data. Probability is not coming from the data at all. Okay, in fact, it's almost like a non-existent quantity. It does not exist, right? It's just that we make some assumptions which assign some real values to our events, and we call it probability, right? So probability always comes from your assumptions, right? So when someone asks you that what is the probability of obtaining 3 heads when you toss a coin 10 times, what would be your answer? Well, answer would be you don't know, because it would totally depend on the assumptions, right? So if you assume that the coin is fair, right, in that case the value of theta is 0.5. Now you can calculate probability of obtaining 3 heads out of 10 coin tosses. Okay, how do you calculate? Based on, again, this assumption, right? So it totally depends on assumption what would be the probability. Okay, so you are only given in this problem when you are asked that what is the probability of obtaining 3 heads when you toss a coin 10 times. Okay, what is this probability? Okay, in order to calculate this probability, you need more information. And what kind of information? You need to know what is the assumption you are making, right? So you need to know what is the assumption behind that, what kind of probability mass function is there which is assigning probabilities to x number of heads, right? So you need to know this, that what is the probability function or the true generative process that is generating these number of heads. That is the one assumption you need to make. Second, what is theta? Okay, so these are the two assumptions you need. Once you have made this assumption and once you have made this assumption, that what is the true generative process and what is theta, then you can calculate probability. Okay, so it is impossible to calculate probability without these assumptions, right? So probability is coming from your assumptions. Okay, so it depends on what assumption you are making. Suppose you do not assume that the number of heads in a coin toss experiment comes from binomial distribution. Let's say it comes from a Poisson distribution. Okay, then the calculation of probability would be totally different, right? And in fact, probability could be very different. Okay, so probability totally depends on your assumption. It is an assumption, right? It comes from the function, probability function you have assumed. Okay, so let us go back to this example. What is the probability of obtaining 3 heads when you toss a coin 10 times? Well, when someone asks this question, you need to ask what are your assumptions, that how heads are generated in this particular experiment. If someone says that number of heads come from a binomial distribution, okay, if someone has told you that this is the assumption, then you need to ask, okay, then what is the value of theta? What is the underlying probability of heads? Now if someone tells you that the coin is fair, then this probability theta is 0.5. Okay, now you have all the information to calculate probability, or not to calculate probability, you should say, now you have all the information to calculate how much probability will be assigned to this event of obtaining 3 heads. Okay, so this probability would be given by n chooses x. What is n here? 10 chooses x, x is 3. Now theta to the power, what is theta? 1 by 2. Theta to the power x, which is 3. 1 minus theta to the power n minus x, which is 7. So this would be the probability of obtaining 3 heads. when you toss a coin 10 times, under the assumption that number of heads come from a binomial distribution where theta, underlying probability of heads, is 0.5. Okay, so this is how it works, right? So the idea is I'm trying to convey here is that probability is something that is you are assigning based on your assumptions. Okay, it is not something you can calculate from the data. Okay? So I will ask you some of these questions in the assignment, that what is the, let's say, probability of obtaining 10 correct responses when you give participants, let's say, 50 words to recognize whether it's a proper word or not. So how many times they would get it correct, right? So probability of obtaining that. Okay? So in order to do this question, you need to understand what is the underlying probability mass function that would give you these yes and no responses, and what is the underlying probability of producing a correct response. Right? So we will practice a couple of such questions maybe in the later in next to next lecture, but this is a very important point to keep in mind. All right, so this is on binomial distribution. Now the second kind of discrete random variable we are going to take a look at is a Poisson random variable. Suppose you are observing how many asteroids hit the moon in a particular year, okay, or how many, let's say, space objects, could be anything, hit the moon in a particular year. Okay, so how many objects hit the moon in a particular year, or let's say in year 2025. Okay. Now this number could be, let's say, 10 or 30, maybe 0 as well, maybe 5, right, maybe 200 as well, right. Actually it depends on in what stage the universe is and other nearby sort of activities. But the important thing here is that it's actually difficult to judge what would be the exact number, especially when we don't know that from where all these objects are coming from. So there are several activities happening in a universe, especially when the universe is chaotic. So it's very difficult, right? But still, what you can think of is that over the years, let's say over the years for past 100 1,000 years, there have been a particular rate with which these cosmic objects, these space objects, hit the moon. Okay, so you can think of an underlying rate of objects hitting the moon. Okay, you can call it, let's say, hit rate or something. Okay, so there should be some underlying rate with which objects hit the moon, right? Now if I have to describe that how many objects hit the moon in an year, okay, let's say this quantity is x. So x number of objects hit the moon in a particular year. Okay, what is the underlying generative process behind x? Okay, so for this kind of data, a distribution, a probability mass function that is very appropriate is called a Poisson distribution. So we say that the number of occurrences in a fixed time period can be given by a Poisson process with underlying rate parameter lambda. Okay, so let's say xi is the number of objects that hit the moon in ith year is given by a Poisson process with underlying parameter lambda, where lambda is the underlying rate with which objects hit the moon, right? So it is the rate of happening something, right? Okay. You can think another example as well. Let's say I want to quantify how many accidents, road accidents, occur in Kanpur in ith day, in a particular day. So I can think that this comes from a Poisson process with underlying rate parameter lambda. So lambda is the rate of road accidents in Kanpur. Okay. So for example, this lambda could differ across cities. So underlying rate differ across cities, and that would determine how many road accidents occur in a day. Okay. So this is another kind of probability distribution that you can think of for discrete random variables. Okay. Why I'm saying discrete? Because this number of occurrences would be a discrete quantity, because the number of occurrences could be 0, 1, but can't be anything between 0 and 1. Okay. So it would be either 0 or 1 or 2. Okay. And it can go up to, let's say, in case of road accident, what is the population of Kanpur, right? So it's a case of discrete sample space. But what is the Poisson distribution? So let us come to its probability mass function. So probability mass function of a Poisson distribution is given by lambda to the power x e to the power minus lambda divided by x factorial. Okay. So if the number of occurrences x with underlying rate lambda follows this probability mass function, then we can say that x follows a Poisson distribution with underlying rate parameter lambda. Okay. So let us take a quick example. So let's say the underlying rate of road accidents in Kanpur is 3. Okay. Assuming that the number of road accidents in a day, let's say xi, comes from Poisson distribution with underlying rate lambda, okay, then what is the probability of obtaining 10 road accidents on a particular day? Okay, so what is the probability of obtaining 10 road accidents? So this would be given by f of x equals to 10 and lambda equals to 3. Okay, so you just plug in x and lambda in this function. So what is lambda? 3. X is 10, 3 to the power 10, e to the power minus 3, this is lambda, and then 10 factorial. So this would be the probability of observing 10 road accidents in a day if the underlying rate of road accidents is 3 and the number of road accidents come from a Poisson distribution, right? Similarly, you can calculate what would be the probability of observing, let's say, 0 road accidents on a day if the underlying rate is 3. Okay, so that would be given by, what is lambda here? Lambda is 3. So 3 to the power 0 e to the power minus lambda, which is 3 divided by 0 factorial. So it would be e to the power minus 3. Okay. By the way, you can draw the graph of the probability mass function. How would you draw the graph of the probability mass function? On x-axis, you would have the random variable, say x, which is assumed to have a binomial distribution such that, Poisson distribution. X comes from Poisson lambda. Okay. On y-axis, you would have probability. So what probability is being assigned to each value of x? Okay. But you can draw the graph only for a particular value of lambda, because as lambda changes, this graph will change. So let's say lambda is equals to 1. Okay. In that case, this graph would look something like this. So let's say this is 0, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. The graph would look something like this. At 0, you would have some probability. At 1, you would have some probability. You can actually calculate what would be the exact probability. If lambda is 1, what would be the exact probability as x equals to 0? It would be f of x equals to 0, lambda equals to 1 would be lambda to the power x, 1 to the power 0, e to the power minus 1 divided by 0 factorial. So it would be 1 by e. Similarly, what would be the probability of x equals to 1 at lambda equals to 1? It would be 1 to the power 1 e to the power minus 1 factorial. So that would be again 1 by e. So actually the probability at 0 and 1 would be equal. Okay. And now at x equals to 2, it would start reducing. So it would be somewhere here. For 3, it would be somewhere here. For 4, even lesser. And then would go very close to 0. Okay, so this is how the probability mass function would look like. Okay? Notice that I'm not joining these points because that would be wrong, because this function is not continuous at all. This function is discrete. If you want, you can join them vertically like this. You can show a vertical sort of graph, but you do not join these points. Okay, because this function is a discrete function, it's not a continuous function. These points are not connected with each other because there is no probability between 0 and 1. Okay, there is no probability between 1 and 2. Okay, so there is probability at only 0, 1, 2, 3, 4 like that. Okay? So this is probability mass function of a Poisson distribution when lambda equals to 1. Similarly, you can draw probability mass function when lambda equals to 2. Okay, in that case, this graph would look slightly different. So maybe probability of 0 would be here, probability of 1 would be here, and then it would start reducing. Okay, so something like this. By the way, you can draw all these things in R. So in R, you can practice these probability distributions. So there are some functions in R. Okay, so for example, let me quickly tell you for binomial and Poisson distribution. So in order to generate random values from a binomial distribution, you can use this function R binom. Okay, you will need to pass on how many values you want, let's say 100. You need to pass on what is your sample size, let's say 10 coin tosses or 10 trials, and you need to pass on the probability, the underlying theta parameter, let's say theta is 0.5. Okay, so like this. Similarly, you can generate random values from a Poisson distribution using rpoise. Here you need number of data points you want to generate and the value of lambda. So let's say lambda is 1. You can also calculate the value of this function, probability mass function, using the function dpoise. So in dpoise, you will give for what value of x you want to calculate. So let's say x is equals to 10 and lambda equals to, let's say lambda, and you can give lambda equals to, let's say 10 or something, right? So this is how you can use these functions in R. We will later on go in detail when I will be using R for all these calculations. Yeah. All right, so this is it on discrete random variables. So we have covered binomial distribution and the Poisson distribution. So these are the more common ones. These are the basically the popularly used cases of discrete random variables, which we will be using for modeling different types of data, especially in this course. So you might be interested and the other distributions might also be useful for you, that you can take a look on at any source. You can search discrete random variables, but these are the two standard ones that are very useful for us. All right, so thank you very much. So this is it on discrete random variables. In the next lecture, we will start continuous random variables. Thank you.